Hello, Physics Nation. My name is Nate Larmond, and I was in a professional development, and we were talking about ideal mechanical advantage and actual mechanical advantage and levers and efficiency. And I don't know, my classmates said, well, let's look at it from Newton's second law perspective. Let's say if this thing is in rotational equilibrium, the sum of the torques is zero. So it was a Zoom meeting. It was really hard to communicate. I'm going to try to summarize my classmate's argument. Let's say the scissors are the load. That distance right there in between this finger, the pivot, and the scissors is a lever arm. So you just take this force, multiply by that distance, and you get the torque, the twisting force that the scissors apply about this pivot, this axis, this fulcrum. Well, obviously, if I let go, it's going to accelerate. So we need to bring this system into equilibrium with a second torque, and I'm going to apply that second torque with my finger, my other finger. This has to apply a counteracting torque. Let me see. The scissors are rotating this thing counterclockwise. That's positive Z from me. So that means my fingers have to apply a negative Z torque or a clockwise torque or an opposing torque. You just take the force applied downwards from my finger, multiplied by this lever arm, the distance in between the pivot, the fulcrum, the axis of rotation, and my downwards force applied by my finger, and that's the counteracting torque. And he said, well, I'm going to do an algebraic manipulation and solve for the ideal mechanical advantage. And it equals the actual mechanical advantage. And, it was a Zoom meeting. Like I said, it was hard to communicate. And that's the purpose of these notes right here. So here's my downwards finger. That's the effort force. Here's the scissors hanging off the other end. That's the resistance or the output force or the load. I know it's annoying that there are three names for these things. In physics class, we call the lever arm the output radius. But in this engineering curriculum, they call it the resistance distance. And again, this would be the input radius, this lever arm right here. But in the engineering curriculum, they call it the effort distance. So, like I said, my classmate was using Newton's second law. So he said if there's no angular acceleration, the sum of the torques is zero. And here's the input torque. Input force multiplied by input radius, subtract the output force multiplied by the output lever arm. And let's see, where's page 2? Okay, he expands those terms and then, like I said, divides both sides by the effort force and then divides both sides by the resistance distance. The ratio of forces is called the actual mechanical advantage, and the ratio of distances is called the ideal mechanical advantage. And this is the argument my classmate was making, and the instructor said, no, machines aren't 100% efficient. The actual mechanical advantage is always less than the ideal mechanical advantage. So he went down a conservation of energy path. He wanted to use the input work and the output work to sort of explain why this is an impossible case. But, my classmate's use of Newton's second law, torque equals I alpha, should work. And I think this is where, the beginning assumptions in his argument were incorrect. He was just thinking we got one torque from the load and a second torque from the effort, but I think there's a third torque. I think the weight of the lever itself, if that is away from the pivot, that exerts a torque. So the center of gravity of this little ruler is obviously right in the middle of the ruler, and if that's away from the axis of rotation, the fulcrum, well, then the ruler exerts a third torque. And then friction, the grinding in between the pivot and the lever itself, that exerts a little torque. So there are actually four torques. And let me see, that's what I'm trying to say down here. The original model my classmate was suggesting was inaccurate because he was missing these other two torques. The torques exerted by the weight of the lever itself and by the friction force. And this is just an algebraic representation of those missing two forces. Thanks for watching. See you in the next video.